Welcome to Malware Analysis for hedgehogs. This is the last part of analyzing polymorphic file infector Virut. Today we will look at the infection procedure to figure out which files Virut infects and when. And we will learn how to compile a suitable PE bait file for PE infection. We will also write a bait file for HTM infection. And we will learn how to force Virut to infect our specific bait file so that we can debug the infection procedure if necessary. So let's get started. So this week we want to find the code that infects files. And last time, in the last video, we analyzed the hook functions of Virut. And we discovered that all of the processes become infected. So functions of NTDLL are hooked in all of them. That means we can open any file that we want with x60 or x32dbg.exe. Okay, so for instance, let's open something like calc.exe. So if we open calc.exe, go to the entry point. Oh, let me make this bigger here. Go to symbols and we navigate to one of the hooked functions. For instance, create file. And there is the hook. So we don't need to debug specifically Virut.exe anymore. We can just look at any of these on our test system. And we will see that these calls here, these are the interesting points where the hook code is placed. Now, I expect that this code is probably doing some more things than just infecting processes, because that's what happens after the process infection took place. And when you set breakpoints in this code here, you need to set hardware breakpoints. We have already discovered that Virut copies itself in the memory several times. And if you set software breakpoints, you are changing the code to an int3 instruction. So if Virut happens to copy this code with the int3 instruction inserted, it will not work anymore in the copied instance. So that's why you should take care. So if you, during analysis of Virut, if you encounter issues that the process suddenly has exceptions, that the code suddenly looks different than before, this is likely the reason that you use the software breakpoint at some point. So what we do instead is we set here a hardware breakpoint on execution. And when we now run the sample at some point, we may arrive here. And at the moment we don't. Let's rerun this. And here we are. So if you restart the sample, it works. And we can see now when we look in the memory map where we are. So this is what we dumped last time. This is something, that's the dump I have here. That's also a reason why it makes sense to save the base address of the dump somewhere, so you know where it has been taken from. This dump, I will throw it into Ghidra, and I will use Ghidra on the host system because this is WinXP. I'm not sure how well it fares with the current releases of Ghidra. So I will switch back and forth between this system for debugging and the host system for analyzing the code statically. So that's what we're going to do now. We note down all of the hooked addresses. So the first address we have is ZW create file, executes this address here. Note that down in some of your one of your notebooks, and do that for the other hooked functions as well. So we have, what else did we have? I think create process was another one, or ZW create process X here. So you see these are different functions depending on which of the hooks are called. You have different actions that happen afterwards. And now I'm switching to the host with this dump here to analyze. So I'm now at my host system, or one of my host systems. I'm drag and drop our dump in here. And now this is a raw binary. Ghidra doesn't know anything about it, and we have to tell it what we want. And I want specifically Visual Studio compiler x86 32-bit code, little endian. So that should be the right one. Press OK, and now we can import this. And open it here. So after opening our dump in the code browser, this is what it looks like. Ghidra does not know where the code is. It also does not know the base address, and that's something we have to fix first. Open the memory map, and there's a little house button here, which will set the image base. Enter that. Save it. And now it should start at our designated base address. And now we can press G and we can go to our specified offset for the hook function. In this case, for the create ZW create file hook function. And when we are at this point, we press D for disassemble, and that takes us to the relevant code here. And we can also create a function. Just like last time, we see that we also need the value of EBP to make sense of the code and to get actual memory locations here instead of these. So let's take a look at our sample here, and we are here at the start of this function as well. And what's EBP? It's 6E428. So let's use this value. And we said OK. And now let's auto-analyze again. And that's what it looks like now. Here is some sort of flag that is set to true or false depending on the value of this here. And if it's true, we do this stuff and we call this function here. And otherwise this is skipped. And then we go into this function. We look at this one. It doesn't seem like much is happening here. Let's go back. But this one, this looks bigger. And this looks actually very interesting. Again, we have here to set the EBP value. But what we also have to see here, this seems to be ASCII. Let's see if we can convert this. Yeah, we can convert this to char sequence. Let's do that. VinC BCUN BC32 PSTO. And here are some more. This says exe with a 0 terminator, and this says SCR. So you need to read it backwards because it's little endian. this is very interesting. A, Z, and a space. When you see that, you should immediately think of turning something upper or lowercase. Because it is subtracting the space, it's an uppercase conversion. And so I'm assuming that we are at the right place. This is the function we want to access because it is checking for file extensions. And I'm assuming that this might have to do with the file infection preparation, so to check which files are appropriate to infect. Let's go back to our VM and try to break in this function here. So let's go there. The function we want to go into is, I believe, this one here. Let's step through, and this is jumping out of this. So the flag is set to false, and we are jumping below this function. So we need to fix this here. Wait, 0 flag, sorry. Go there. And now we go inside of this function. And we are there. Now we can note down the value of EBP and set this in Ghidra. So it's 72D2F000. Okay, 72D2. Set register value and 72D2F00. Press OK. And now let's auto-analyze again. So this is the file infect function, I'm guessing. Infect. Let's go back because we know that this is the hook function for ZW create file. We can actually also set the correct parameters here. We just copied the ZW create file definition for this function and use this here as well. So if you do this like that, it will ask you for the where those types are. So let me do that quickly, and you will see that some of the types cannot be resolved because I don't have these structures inside of any of my databases here. So we press continue editing, and we change those structures that we don't have yet into ulong. Let's try this. There's another one where, I have a comma here that I need to remove. Now again, press enter. And we set this to standard call and press OK. And now we can see which of the structures are actually used. And we see that this IO status block is one we also should probably add, at least if we want to understand this part of the code here. By figuring out the definition of the file infect function, we have done an important step, because this file path is one we can now manipulate to point to our own bait file or goat file. A bait or goat file is an analysis technique that people use to analyze virus infection or also ransomware encryption. So these are test files specifically designed so that the virus infects them. And They make analysis of infection functions or encryption functions easier. We will also set up such a bait file, but before we do that, we actually need to figure out what files are appropriate for this virus. So what kind of files does it look for? We already have seen this here. Oh, for some reasons, these are... We already have seen this here, that it looks for certain strings. Oh, it seems like there are more. Okay, so we see here exe, scr, we see htm, php, and asp file extensions here. So we can guess that there is probably two types of files that this virus targets, which is the first is like PE file, and the second is some sort of script file that it targets. Let's start with something simple. Let's create an HTML file and see what the virus does. But before we continue with that, let's resolve the APIs that we didn't resolve yet here, because we created a new dump. So in this dump, the API tables are not resolved. And we see this, for instance, here. This is a function which is set by this value. When you double click that, you can see our API table. Let's now use this address and go there in x64dbg. And what you can see here, so if we, let's say, log this value here, we see it's get module handle A. And if this is the start of the table that we already resolved in the last video. So we already have a script. We just need to modify it a little bit, because these addresses are now, they have a different base now. And we can simply fix this and then apply it here as well. Use the very same script. So this is our script. And the way we deal with that is, so firstly, do the kernel APIs. So the old base of this table, just take the very first value of that. And for the new base, we take the new value, which is, let me check. We look at this table. So this was get module handle A. So this is our new value. A1257. And then we say we subtract this old base and add the new one. And then we do the very same thing for ntdll. Now in this case, I used the base address of the table itself. We could have also used the base address of the memory region instead. It doesn't really matter. Just and the new one, when we check again here, that is 363. and we open our script manager. Python Virut install table. Okay. Copy this here, save it, and run it. Let's see. This is how it looks like. And I did a mistake, so let me revert this shortly. The mistake lies in here. We want this to be kernel 32. Yeah. So now we got this, and we say in here apply function data types. Now let's go back to our file infect function, and here are the resolved APIs. So this is nice. So here is one global variable that is set to 0 for all of these cases and set to 1 for this case here. So this is some sort of Boolean which will, so interestingly, these two cases here are PE file cases. So it's set to 0 for PE files. And these cases here are scripts. So I would say, since it's 1 for a script, I would say this is like a check if it's a script file. Is script file. So let's see where this takes effect. Let me go here. Where is it used? So it's red here. Okay, it seems a little bit odd that it's not used here, but maybe the code is still not decompiled that uses this one. So what is happening here? We have some function calls that may perform the actual infection. So let's go into these. And this still needs an EBP value that's appropriate. Let's go back. Let's go to this one. Nothing noteworthy. So the next interesting location to look at is here. But before we do that, let's use the EBP value that we have in this function. Let's use it for that one as well. So we go back here, copy the value, and just see if that one works. So here you see a call and then a kernel 32 DLL. So the call to this function does not return. We can stop here. Let's now set the value. And let's also edit this function signature here so it does not return. And we can see now that this worked because we have here a get tick count call, and that means it aligns with our data. Auto analyze. What we also see is the check for is script file, which is done at this point. If this is a script file, it is calling this function, and if it's not, it's doing this here. And that makes sense because here is the MS-DOS MZ signature. So we can see here, if we convert this to a char sequence, this is MZ. And we can also say we apply here an equate. And there you see an image DOS signature. And that means that this part here is the start of the PE file or the start of the file. So let's use proper names for these functions now. The function above this one where am I? I meant the file infect function. So the file infect function, this is actually search, check, and infect. Let's call it check and infect. And this one is, well, it takes a long time to decompile. Infect file. So the first one checks if the file is an appropriate file that it wants to infect. And here it is sure that this file should be infected, and then applies one of two methods to do that. The first one is this. If it's a script file, you have infect script file. And the second one is here, where it starts processing or parsing the PE structures and probably also infecting using these structures. Let's see if we can read a little bit more with applying the appropriate types here. So this is the start of the file. However, when you check this, it starts 2 bytes after the G start of file. So let me correct this a little bit. So this is probably all file data, so we clear that. Here. So it starts 2 bytes after that. And that means we apply an adjusted pointer offset with offset of 2. And for the image DOS header structure like this, I name this adjusted DOS header. Let's see if that works. Yeah, that looks good, because you see now it's not one E3C here, and that is ELF new. So it checks if ELF new is set, and this then checks the PE signature here. So this is the base address plus ELF new, and that is the PE headers. PE headers. Right, so you can probably set an equate here, image NT signature. And correct the type here, which is image NT headers, like this. And now we can see it's checking here characteristics, say set equate. I'm searching for characteristics. We see image DLL characteristics, WDM driver. So it's checking for that, and it's checking if this is not 0. So if it's a WDM driver, it goes to this location. And or if it's a specific subsystem, C subsystem, this one. If it's the graphical user interface subsystem, if that one is set to 0. So if it's not if it's not Windows GUI subsystem, it also goes to this, and this is at the very end. And we see here a lot of unmap, view handle, close handle. So this is like yeah, something like close and exit. Get that back there. So that's already interesting. Then we have here a timestamp. Timestamp check. And it expects a very specific timestamp here. So seeing that this does a lot of stuff, if the timestamp is not present, I'm assuming that this is the infection marker of Virut here. Virut's infect marker. That's a flag to check if the timestamp is lower than the infect marker. And here probably does the infection happen or something like that. So we already know now, we know more now about the kind of PE files that Virut expects. So it will not infect WDM drivers, and it will only infect subsystem Windows GUI files. It will not infect files that have this specific timestamp here. So now let's try and get Virut to infect a bait file that we place. And we are going to create a .htm file using Notepad. Here I have an old version of Notepad++ that still works on WinXP. Our stub is a very simple HTML stub. I saved it. Of course, we need to save it with HTM. Let's open this. Seems to work. And now we will try to force Virut to infect this file specifically when we debug it. So I'm currently at the entry point. And what we will do is we will write a script here. And the script, let me open Notepad. Reaching at HTM. This is the script. First thing, we will clear all our breakpoints, and then what we did is we went to the symbols ntdll and checked where ZW create file is, because here's the call to the function that will infect those files. So this is where we want to place our breakpoint, and we need to use hardware breakpoints. Run there, and now we will try this. Where did I save this? Let's save it on the desktop. So run this. And we are at this location. So what we do now is we actually want to go in here. So step into, and we are at the start of this function. And now where we want to arrive is here at the function that starts to infect those files, where we determine that the file path is in ESI. So let me see what we need to do. So there was this jump, which jumps over that part that we want to execute. So we will have to fix this part here. We go to this location, copy address, and we say we run onto this address, and then we want to skip this instruction, this JNE instruction, so that we can arrive at this place here. So we say skip, and we want to go inside of this call. Let me copy this address as well. So this is the check and infect files function. And we run until we are there at the start of this function, and then we clean the hardware breakpoints. So let's restart this and test our script. Reload the script, run. And we are there. So this is the check and infect file function. We see here is the conversion from lower to uppercase. And now we want to force that it uses our bait file and not the file that is currently inside here. So let's do that. One thing that we need to do though, full on dump, we see this here, we only have this much space for the path. We don't have more. And because of that, I'm gonna place the bait file in a location where the path is short. So let me use this, and I'm gonna drag and drop it in here. Let me verify that it's not already infected. This looks fine. And now we will change the path. So this is our path, right? This is the path, and it's mega HTM. Now, I don't know an easy way to put this into the dump except for using move operations. So if you know something that's more simple, let me know. But what we will do now is, it's an ESI, so we will use move operations into ESI to change every part of this path. So let's do that. First, I'm going to convert this to hex. And we split this. And so on. So and we move this to ESI, and because it's little endian, we actually have to revert the order of them. So let's, for instance, test this command here. And now we see it has correctly changed the first 4 bytes of characters. Yeah, so let's do the rest the same way. So for testing, I'm going to execute it here in the command window. And this looks good. So now we have changed the path to our bait file. And this will do this for us here. And we can then continue to analyze this. Now the question is, if we now run this, so we ran this, does this change or infect this file here? And it does not. It still looks like this. Maybe there is another check that fails, so the infect file function or infect script file function is never called, or this file doesn't have the correct structure. Let me see what happens if we just step by step execute this. So let's reload the script and run. Following this assembler. So we are here at the infect file function, correct file. Let's see how we can force this to infect the file. So this is turning this into uppercase. Let's put a hardware breakpoint here like that and remove it again. Now there is this check. So this is returning. I'm not actually sure what this is doing, like what kind of check this actually is. But I don't want this to return yet. I actually wanted to call one of these, I think, I'm not sure which function was, maybe the first, but one of these functions was the infect file function. So let's test by just not taking this jump and run it. And now let's see again if the infection worked. And now it did. So if we just change this jump, we also get it to infect this file. Let's remove this again. And rerun. So it was this one, and this jumped. Was it this one? No. Let me do this again. This one. So we skip this call here. We say copy address. And skip this check. And then we should be successful with this. So let's rerun everything. Go to the entry point, reload the scripts, and run the script. Following this assembler, we are here now And if we run this, it infects this file. So this worked very well. This is an iframe, so we didn't see this in the Explorer for some reason. But so yeah, this worked, and now we are set to debug this code as much as we want. And we can also easily replace this file, for instance, with a PE file if we want to debug the code that infects PE files. Next, we generate a bait file for Virut that is a portable executable file. And we figured out some things that must be true for such a file to be infected by Virut. And one of those was the subsystem. It requires the Windows GUI subsystems. You see above here, I made some notes how to compile and link this file. So we are using YASM, and the linker then supplies the subsystem. Because of that, I also decided to use a message box to display a hello world instead of printing it to the command line. And to have a slightly bigger file, I added ample zero padding everywhere. So we have the data section with our two strings here for the title and the message, but also 4 kilobytes zero padding. Additionally, we also do the same in the .text section. And last but not least, there is an empty .foo section, which is 64 kilobytes. So I also made a make file, which just does the same as discussed here. So compiling and linking. See here is the compile step and the link step. And we have an install command here, which will copy our resulting file into the share where Virut can infect this file. So this is the path we are going to use for Virut so that it infects our file. You can see some link flags I'm using here. One is fixed. This gets rid of the relog table. I don't need the relocations in there. I actually want to reduce the amount of data as much as possible so that I have mostly zeros in this file. Also, here is debug none to avoid some debug data. The main is our entry point main function, or the label here, which is this one. And we need those two imports to call message box A and exit process. Now, to create the file, I just need to call make. And because I already did this, it says nothing to do. Repeat this. So we say make, and we can say make install, and then we have copied our file to the correct location. So let's take a look at the file that we just generated. And this is the file here. So you can see we have lots of 0 bytes here because everything's black. Black means these are zeros in this byte plot here on the left side. And in the middle, this is the entropy, where black means there is 0 entropy. So there's nothing, no change in this area. It seems that our linker or compiler added an .r data section. That's a section I did not specify explicitly, but it put inside the debug info here, which is this data here. This kind of belongs to the common object file format. I have no immediate way or easy way to prevent this from happening. So we have to live with this, but it's fine. It's not so much. And we can recognize it when we see it. So the imports themselves are here. So we have the message box A from user 32 and exit process from kernel 32. So I guess that's it. That's everything. Or maybe this is interesting as well. We see here the sections, we can see everything's in order. We have execute and read permissions for the text section, whereas the other sections do not have any execute permissions. This is important because viruses very often change the last section specifically. This is also why I put the section there with only 0 bytes. So if any change happens to the last section, this is a section that doesn't contain anything anyways. So yeah, let's go for it. Let's try to infect this file and see what happens. Now we are back in the VM, and I did a small change to our x32 dbg script. So we just needed to change these values here, which is the extension. But before that it was HTM, now it's exe. So you just change those 3 values and the script should work. And now let's just restart this and go to the entry point and run our script. So now we ran, and we can actually, let's see if we got the right one. So you see here, this is now telling Virut to infect this file right here. And if we now just run, this file should be infected. So this is our mega.exe file that we just infected. So let's take a look at the visualization. We already see a difference here, and that is the end of the last section has now very high entropy here. There seem to be like 2 data blobs. I'm not sure why these are 2. And after these high entropy data blobs, there is the dot for the entry point. And that might be difficult to see, but if you go into the section table, you can see here, okay, last section is now execute, read, write permissions, which is very unusual. And the entry point that we see here in the optional header Windows field is in section 4 with name full. You can also see this in the anomalies section. So one of the main reasons why antivirus products find it suspicious if the last section is readable and writable and executable is virus infections. Viruses usually infect the last section. And that's also when I did my master's thesis, I generated, like, I have added these as anomalies here so that it can potentially be used for classification of malware. So just from using the bait file, we have already learned a lot about this virus. And that is that it appends itself to the last section and that it changes the entry point to the last section. If you read some analysis reports on Virut, you will see there are different infection strategies used by this virus family. So sometimes it may also use the original entry point, but insert a jump to the virus entry point there. So this is also possible and happens in some cases. So what did we figure out today? Whenever ntcreate_file is called by any of the infected processes, Virut will check if this is a file that it wants to infect. And Virut infects files with .exe or .scr, screensaver? Yeah, scr extension. And it will infect those files only if these are no drivers, if they don't have specific strings in the file path. Those are the strings that we saw here. If they have the WinGUI subsystem, and if they don't have a very specific timestamp. This timestamp is an infection marker. This prevents Virut from infecting a file twice. Virut will also infect a set of files that are script files, so it will infect .html, .php, and .asp files. Into the HTML files, it inserts an iframe, which redirects the browser to a specific address. Now, we did not look at the actual infection routine yet, so that decides how to infect specific files, only at the part of the routine that checks which file to infect. However, at this point, we should know everything that we need to analyze the rest. So there are not more tricks or techniques. The rest is just grinding, marking up code, debugging. You have all the tools that you need now. If you're looking for a longer project, you may also consider writing an open source disinfector for Virut. I think this is a very challenging task and very interesting as well. If you made it to the very end here, you're probably one of very few people. Please let me know in the comments below.